Welcome back to Applied Mathematics. This video is titled Lines and Angles. We're going to be going through some of the basic rules of geometry, some basic vocabulary. Let me get my head out of the way, and we will start at the very beginning. The first definition of geometry tells us a point is. Period. End of sentence. Not a very descriptive statement. And to a large extent, that kind of serves the purpose. A point is an intentionally generic object. We're not going to try to define what it is. We're not going to try to think about what it is. We're going to depict points by drawing dots on a page, but I mean, that's just a picture. That doesn't really tell us much of anything about it. But we will use points as our foundation. To talk about a line which is determined uniquely by 2 points. And this is kind of a problematic definition in ways. Given 2 points, there is exactly one line that passes through those 2 points. By convention, we're going to take the word line to mean something that extends indefinitely. And if I name these 2 points on the line, A and B, I can write the name of this line as AB with a double-headed arrow above it. If I name another point on this line, let's say that that's point C, then I could just as easily name this line as AC, or as BC, or as CB. Right? The order of the 2 points does not matter. If there's more than 2 points, you can name it using any of them. That's all well and good. For our purposes, though, lines usually aren't all that valuable. Some of the properties, some of the ideas behind lines that extend indefinitely are going to be important for us. But for most of our applications of geometry, we're going to deal with line segments, which are a finite portion of the line. A line segment is the portion of a line between 2 endpoints. So if I have my point A and my point B that I've already been talking about, and I want just this much of the line, I can describe that as line segment AB. I put a bar over it without arrows to indicate that this is a segment. And then when I have a segment which has a finite length, I can talk about that length. Call it AB. The length of line segment AB is the distance between point A and point B, measured in your units of choice. One of the places that things can get really confusing for students first studying some of these ideas in geometry is the fact that I used 2 letters here, right? The length of line segment AB I have written as AB. That is a single value that uses 2 letters as the variable name. right? It's not variable A and variable B. The entire variable is AB. You need both letters to be talking about this measurement. All right. So that gives us lines. One last kind of thing related to lines is a ray, which has one terminal point. Let's go ahead and call that Q, and then extends outward indefinitely. And if you can find some point to give the direction in which it goes, we can talk about QP as a ray. If I have another point out here somewhere, like say this point R, I can draw another ray that also has the terminal point Q, calling them coterminal rays. Right? The terminal point of a ray is the point where it stops, and I've drawn two rays here that stop at point Q. So QP and QR are two coterminal rays. Two coterminal rays form an angle. The space here, the way at which these two rays separate from each other, is called the angle. And there are several ways of talking about and classifying angles. In this class, we're going to use the degree measure of an angle. And the degree measure of an angle is formed based on two rules. The first rule is that a straight line is a ray with measure 180 degrees. Right. Thinking about a straight line as a ray, or as an angle, seems a little bit counterintuitive at first. So let me try drawing on top of this line. Right, let's put a point here. Let's draw a ray going out that way, and another ray going out that way. The second rule, if two lines intersect to form four angles, all with the same measure, then these angles are right angles and have measure 90 degrees. All right. Those two rules determine the idea of degree measure, and anything else we can talk about with degree measure falls away from them. I'm not too worried about degree measure in and of itself in this course. I will mention that there is an object called a protractor that can be used to measure an angle. We're not worried about that in this course, so just knowing that that is a thing that exists and you are likely to come across it in a future course is a good enough place for us for right now. Instead, I want to find some more qualitative ways of comparing angles, and a couple of quantitative ways too. The first one is classifying angles. And there are 3 vocabulary words for talking about angles: acute, obtuse, and reflex. An acute angle is somewhere between 0 degrees and 90 degrees. So maybe something that looks a little bit like that. An obtuse angle is between 90 degrees and 180 degrees. So maybe something like that. And a reflex angle is between 180 degrees and 360 degrees. Reflex angles are kind of strange because honestly, they look a lot like acute angles or obtuse angles. But instead of measuring the inside part of the angle, we measure the outside part of the angle. And it's important to remember that reflex angles exist, because when you have 2 coterminal rays, they don't form just one angle, they form 2 angles. Related to that, we often see angles classified as being complementary or supplementary. 2 complementary angles together form a right angle. So an angle here and an angle there together forming a right angle are called complementary. I am not going to mention complementary angles again this semester, but for anyone who is moving onward to study anything further in mathematics, you're probably going to get to trigonometry in the near future, and complementary angles become very important at that level. The other one here, supplementary, these are going to be important to us in this course. 2 supplementary angles together form a straight line. Very often in the work we're going to be doing, we're going to be able to look at a situation and talk about 2 angles being supplementary. So if we know something about one, we immediately know something about the other. Vertical angles, I've seen a couple of different definitions for. I think that the most clear one is that vertical angles are angles which are not supplementary at the intersection of 2 lines. So if I draw 2 lines that intersect each other, those 2 lines together form 4 angles marked out here. Let's name them angle A, B, C, and D. Now, if you look at this picture, angle A, just realized I haven't mentioned this symbol yet. This symbol that kind of looks like an L is supposed to be kind of a 45-degree and then a straight line across the baseline. I'm very, very good at writing these out, and they are always clearly angle marks and never capital L's. But that's just the symbol to emphasize that the thing I am talking about is an angle. I'm talking about the picture on the page, angle A. Angle A and angle B together form this straight line, and so they are supplementary. Likewise, angles A and C are supplementary, angles B and D are supplementary, and angles C and D are supplementary. Each of those pairs together forms a straight line. All right. So which pairs are left? Well, we've matched A with both B and C, but we did not match A with D. Angle A and angle D are vertical angles. We've matched angle B with angle A and with angle D. We did not match angle B with angle C. So these two are also vertical angles. At this point, I always am left wondering, how did we come up with the name vertical angles? There's nothing vertical about the relationship between angles B and C, and unfortunately I don't have a better answer for you than it's just the word we use. So try not to get tied up on that. The word vertical here does not have an association with horizontal and vertical in any way, shape, or form. It's the name of angles which are not supplementary, formed at the intersection of two lines. But vertical angles have a very interesting property. Let's consider angles B and C. We know that these are vertical angles. We just said that. But think about their relationship to one of the other angles. How about A? Because B and A are supplementary, if you add them together, you get 180 degrees. Because C and A are supplementary, you get 180 degrees. Right? Two supplementary angles together form a straight line, and a straight line has a measure of 180 degrees. Now watch this. The transitive property of equality says when you have two equations that are both equal to the same thing, then the other side of the equations are equal to each other. B plus A has to be equal to C plus A, and then if I just subtract A from both sides of the equation, I get that B is equal to C. I know absolutely nothing about angles B and C except that they are vertical angles in a picture of two intersecting lines. And without too much work, I find it is forced that they have equal measure. Vertical angles always have equal measure. All right, moving onward. The next structure that we're going to need is parallel lines. We say that two lines are parallel if they never intersect each other. And at first, this statement doesn't seem all that profound, but I do need to remind you that when I talk about lines, I mean things that extend indefinitely. Right? If I draw a line segment like this, and I draw another line segment like this, these two line segments do not intersect each other, but if I extend them out, they will intersect each other in not too distant of the future. So even though the line segments, the part that I drew, does not intersect, the lines, the infinitely long things that they represent, do intersect at some point. So two lines that never intersect each other must always remain exactly the same distance apart. All right. Up next, a transversal. This is one of those vocabulary words that messed with me for years after the first time I saw them. I was convinced that there was something profound going on here that I was missing. A transversal is a line which intersects several lines. There's one. There's another one. I have two lines here. I have intersected the two lines with another line. That other line gets the label of transversal just because it has done that. When I have two lines intersected by a transversal, and I'm going to redraw this picture just so I have a little bit more space around those two intersection points to draw things. I want to draw your attention very closely to the point of intersection between the transversal and each of the two parallel lines. In each of these pictures, we have four angles: top left, top right, bottom left, bottom right. Top left, top right, bottom left, bottom right. The idea of corresponding angles comes up in a couple of places in geometry. Specifically here, I'm talking about corresponding angles for parallel lines. Looking at these two pictures, the angles that are in the same relative position. So in this case, it's angle A and angle E, angle B and angle F, angle C and angle G, angle D and angle H. Those are four pairs of corresponding angles. Just like with vertical angles, corresponding angles are an important vocabulary word because corresponding angles always have equal measure. Unlike with vertical angles, I don't have a nice trick for showing you why this works. In fact, this is one of the fundamental ideas of geometry. The Euclidean geometry, the geometry that was studied by the ancient Greek mathematician Euclid, is based on a couple of fundamental ideas. One of them is the definition of parallel lines, which his definition was a little bit awkwardly worded, but an equivalent modern definition is that two lines are called parallel if and only if the corresponding angles all have equal measure, which I think is a great definition. That definition forces our geometry to be a flat page, right? The screen that you're watching this on, well, for most of you, unless you have a curved monitor, the tablet that I'm writing this on, the page that you are taking your notes on. These are all flat surfaces. They behave under the Euclidean geometry. You can actually change this rule around a little bit, and you get other kinds of geometries. Spherical geometry is always very interesting because that's the geometry that takes place on the globe. And spherical geometry is notable because there's no such thing as parallel lines. Think about lines of longitude on the globe. They all intersect at the poles. You can actually go the other way as well. You get hyperbolic geometry. And to me, in southwestern Pennsylvania, hyperbolic geometry is incredibly useful because hyperbolic geometry describes rolling hills and valleys like what I see when I look out my back window. If you're really interested in studying non-Euclidean geometry, there's a ton of fascinating ideas out there. Some of them are very accessible. For our purposes this semester, though, I just don't have enough time to talk about them. We're going to remain in the world of Euclidean geometry. All right. Looking at this picture a little bit more closely, though, I want to point out something else. If I look just at this one picture, this one portion of the two parallel lines cut by a transversal, I'm looking at intersecting lines, which means that I have a pair of vertical angles that have equal measure, and I have another pair of vertical angles that have equal measure. All told, in the picture of two parallel lines cut by a transversal, and I'm just going to draw it in a different orientation to get you accustomed to thinking about parallel lines in all sorts of different directions. Here I have another two parallel lines cut by a transversal. I've got these four angles that will all have the same measure. And then I've got these four angles that will all have the same measure. There's a bunch of special names for different pairs of these angles. For example, let's call this, I don't know, A, B, C, D, E, F, G, and H. Right. For example, angle C and angle F here are what are known as alternate interior angles. Angle D and angle E are what are known as alternate exterior angles. Angles B and C are same side interior angles. Angles A and D are same side exterior angles. You may have in the past taken a course in geometry where you were forced to memorize those kinds of relationships. If you have those and you have the vocabulary, I encourage you to use it. If that vocabulary sounds intimidating and you feel like you've never seen it before, or you kind of remember seeing it before, but you don't really remember how it works, don't worry about it. You don't need it. The important thing is that when you look at this picture of two parallel lines cut by a transversal, you can identify that there are two sets of four angles, and each of those sets, all four angles, has the same measure. That's the only thing we're going to care about. Can we identify in a picture a bunch of angles that have the same measure? All right. One last thing that I want to talk about before we wrap up. That thing is a triangle. And I am drawing this triangle very sloppily, very intentionally. You probably are familiar with the fact that the three angles in any triangle have a total measure of 180 degrees. What may surprise you is that that's actually very specifically a property of Euclidean geometry, geometry on a flat page. If you try to draw a triangle on the surface of the Earth, if it's a large enough triangle, you will be able to draw one that has a total angles more than 180 degrees. In fact, I really like one particular triangle that has 3 right angles in it. Start at the North Pole, continue along the Earth until you get to the equator. Take a right turn and walk along the equator a quarter of the way around the planet. Then turn back north and finish up. You end up at the North Pole right where you started. 3 sides, so it's a triangle. You made a 90-degree turn at each of the corners, so it's 3 right angles. That's not a total of 180 degrees because you're not on a flat sheet of paper. But that kind of thing is very important if you want to do airline navigation. Right. A demonstration of why that is the case. Let's take a look at this triangle. I'm going to go ahead and name the 3 corners of the triangle as A, B, and C. And I'm going to draw a line through C which is parallel to AB. Now that I have done that, I have 2 parallel lines cut by a transversal. And in that picture, this angle and that angle, those are the alternate interior angles, but again, the important thing is that they are going to have the same measure. I can also look at those same 2 parallel lines cut by this transversal and realize that those 2 angles have the same measure. They are also alternate interior angles. All right, so this is angle A, this is angle C, this is angle B. Together, they give us a straight line, so together they have to add to 180 degrees. All right, it's a conclusion that we knew was going to happen. I said it at the start. The reason I wanted to walk through this with you was to demonstrate that the fact that the 3 angles of a triangle add to 180 degrees is entirely dependent on that rule about the angles of 2 parallel lines cut by a transversal. If we lose that rule, like we do looking at a sphere, looking at the surface of the Earth, then we lose the idea that triangles add to 180 degrees. All right. That was a lot of vocabulary in this video. I didn't do a lot of calculation. The calculation that I am missing is entirely just arithmetic. Take 2 things, add them together to get 180 degrees, so subtract the one you know from 180 and you get the other one. That's not really the interesting thing about this. In the next video, we're going to be using the ability to identify angles with equal measure as a way to build more complicated structures. For now, I think that was enough to go through. Thank you as always for joining me. I'll see you next time.